Hey, thank you. Hey, everyone. Yeah, it's my great pleasure again to introduce Dr. Dylan Colvin. Is a collaborator of mine here at the University of Central Florida, and so it's a great joy for me to introduce him. He's one of the assistant research professors here at the Florida Solar Energy Center, which is a research center of the University of Central Florida. And the center is located in Cocoa, Florida. So just a little bit of background about Dr. Colvin. He is a graduate of the University of Central Florida. He actually has a Bachelor of Science in Mechanical Engineering that he obtained in 2019. And he obtained his doctorate degree, his PhD in Material Science and Engineering in 2022. He has been studying photovoltaic module reliability at the Florida Solar Energy Center for 7 years. And he actually started here as an undergrad research assistant, characterizing PV modules or solar panels. He has experience with different methods of measurements for those solar panels. So he's going to talk about it. He's been doing optoelectronic imaging, flash testing. He does also image and data analysis, as well as field measurements. In today's talk, Dr. Colvin will give an overview of various measurement techniques and analysis tools to study solar panels. And he'll mention how those tools help us basically to characterize the device performance as well as the degradation of those performance over time. He's going to mention also some other techniques that he used to analyze degradation. These involve sometimes coring samples out of solar panels and then doing some additional micro characterization techniques to basically study the materials and understand how those materials degrade over time. So without further delays, Dr. Colvin, we look forward to your talk. And the title of his talk is Using Photovoltaic Module Characterization to Research Reliability at the Florida Solar Energy Center.
All right. Well, thank you for inviting me to speak. Thank you all for coming. I'm excited to talk to you a bit about some of the solar energy research that we do and just give the bigger picture of solar energy and all the really interesting ways that we can measure them and get tons of really cool information out of it. So, obligatory UCF slide. We are quite a large university. The main campus is in Orlando, and as Dr. Senior mentioned, my second home is here in Cocoa at the Florida Solar Energy Center. And to take a step back before we get into some of the details for all the measurements we can do, I wanted to give a bit of background into the climate of solar energy and renewables in general. So there's lots of opportunity in renewable energy. Of course, I'm focusing on solar, but there's hydroelectric, there's a lot of wind, and tons of solar. In 2023 alone, $600 billion was invested in renewable energy. And on the plot on the right, there's a forecast for solar energy in particular to increase by at least 3 to 4 times its size. Now, one of the interesting things that I've noticed and others in this industry have noticed is that there are a lot of groups who will forecast how much solar will get installed, and every time they underestimate how much will get installed. So we've got these nice forecasts, but the chances are we might actually see even more growth than anticipated. So lots of opportunity, lots of money going into this industry, and lots of and a large need for trained workforce. And so one of the things that we do is install a bunch of solar panels on our different sites to track their performance over time to see how they do. So we've installed and measured tons of different technologies, shapes, sizes, conditions, you name it. And one of the things that we've looked at is how are they installed, what conditions, and how does the environment affect the solar panels. They're all qualified according to different standards, and there are accelerated tests that do a good job at simulating years and years of outdoor exposure into weeks or months. But there's nothing quite like just having a solar panel sitting outside and watching it respond to the environment. So some of the panels that we have been outside for well over 10 years. Some of them that are newer have been out for a year or so. And we have a pretty decent flux of modules coming in, coming out to test and tell the industry, this is what we're seeing. But taking another step back, what is a solar panel? We know them as this thing that you shine light on and you get power out. And of course, we know it's more complex than that, but what is really cool, they're a material system. There are all sorts of different materials that are used in it. And they're not just reacting to the environment, but they're interacting with each other. So it's like this really fun puzzle of studying their degradation and trying to figure out why they're doing what they're doing. There's the whole research and development side that looks into squeezing out every little bit of efficiency possible from these materials. But there's an offset. There's often an offset between how efficient you make something and how long it lasts. And my focus is mostly on the reliability side. So we look at older technologies, but we're also looking at newer, more contemporary technologies to see, are we moving in the right direction? And to give a little bit of an overview, this is historically the module architecture that you'll probably see most, since we have decades of panels that have been outside. And the more contemporary technology is not too different. So you have this sandwich where you have these, they're called cells that actually produce the power, all sandwiched with polymer layers, a glass polymer or two glass layers, and then wrapped together with an aluminum frame. So we're used to seeing glass on the front, then you have the cells and then polymer backsheet, but the industry is largely moving towards replacing that backsheet with another sheet of glass. And that in large parts to help insulate those cells more from the environment, but also to help with its mechanical resilience to impacts like hail or heavy weight like snow or wind loads. So we look at every one of these materials in our research. We look a lot at the cells, but we're also, we have to pay attention to every layer. So there's lots of fun to be had. So at the Florida Solar Energy Center, I'm managing the photovoltaic module characterization facility, or as we affectionately call it, the lab. Here's where a lot of the fun happens. So there are a couple widely standard methods of measuring solar panels. That's flash testing and what's called electroluminescence imaging. And I'll get into that in a minute. So flash testing, as you might expect, flashlight, see what comes out. And so, solar panels are often qualified and described in terms of one curve at one light intensity. So what we get out of the splash testing is a current voltage curve. So by looking at all these points, looking at the shape of the curve, looking at the values, we can get a pretty good idea of how is the panel performing and why doesn't it have as much power as we want it to. So we don't just take this current voltage characteristic curve at one light intensity, we do it at hundreds. Because the solar panel is not going to see one light intensity. So we want to look at how efficient is it at all sorts of different light intensities, whether it's no clouds in the sky, beautiful sunny day, or a bit more cloudy. So one of the things that our flash tester measures is called a sun's VOC curve. So it's taking it's a totally open circuit, so there's no resistance in the circuit, well, infinite resistance in the circuit, excuse me. And you're just measuring that voltage as a function of light intensity. And you can get a kind of, we'll call it a type of efficiency versus light. It gives you an idea of how well are you getting that current from the device. In a way, how long does that current exist, but at a more diode cell device level. But you can also get a sort of ideal IV curve using the sun's VOC technique. So when we compare this ideal to the actual, and we can get some other useful parameters out of it. Particularly how much series resistance is going through, is within the module. Now this is flash current voltage. You can do current voltage in the dark. I mean, solar cells are diodes, and as a vestige from the diode industry, dark current voltage was the most common technique to measure solar panels and solar cells, because that's the technique used to measure diodes. So we still do dark current voltage on solar panels, but people don't look at the data as much as flash testing. So moving on to luminescence imaging. So solar panel is just an LED backwards. You can put light in, get power out. We can put power in and get light out. It's just that light's in the near infrared, so we need special cameras to image it. So all of these, this contact corrosion. So on the cells, they're called bus bars, and you can see them here. Those are the main metal contacts that's extracting most of the current and transferring it. So you can see those contacts corroding. You can see cracks in the cells. You can see just how damaged a shattered panel is. But if you look at it with a naked eye, it looks just fine. You can't see any of this just by looking at a panel. So I think of electroluminescence images, power in, light out, as kind of like an X-ray into your solar panel. Photoluminescence is similar, since it's just you shine light and you get light out. But each technique can show some different things. So like with electroluminescence imaging, there's power going through it, so those resistances manifest. So by comparing electroluminescence and photoluminescence, you can start decoupling some defects between the two. They complement each other very well, and there are lots of quantitative analysis techniques that have been developed over the years to get more information than just, that looks pretty bad, that looks decent. Excuse me. I have to give a little bit of background because a lot of my PhD work was focused on electroluminescence image analysis. So one thing that we can get out of these images is a metric for performance. I mentioned dark current voltage. In that case, you're applying different levels of voltage or current, and you're measuring the other. You're applying different levels of current, different levels of voltage. You're measuring the current output and the voltage. And you can get a curve that it looks very much like a flash test current voltage curve. But they can show some different features between the two. Well, you can get that dark current voltage curve for every one of these cells, not just the panel, just by taking a series of electroluminescence images. You can use the brightness levels of each cell as a way of getting the voltage that that cell is operating. And using the current that you're applying to the panel, we're assuming all these, for all cells that are in series, same current through every cell. Now you get a voltage. Take a bunch of images, and now you've got this nice curve that you can analyze and start getting some performance characteristics out of them. And so we developed another technique that builds upon this and not only gives you this overall performance of every cell, but even at the pixel level within the image. And we're looking more and more into machine learning. So I and many others manually annotated thousands of these images to look at specific defects. And then a previous student of ours developed a machine learning model to take those annotations and predict them on any other electroluminescence image. And we saw good results. So these are just a collection of some of the defects that we can see in these types of images, whether they're different cracks within the cells themselves, some issues with the metal, and other issues with the metal, but a little more specific to what's wiring every cell next to each other. So we have these techniques. Well, we can apply those techniques even while stressing the module. So there's something that one of the quality assurance tests for solar panels is static and dynamic mechanical loading. In this case, this is our load spot that we, Price by Automation developed for us, and it can perform these load tests. Like you're seeing here, we're just seeing tempered glass bending like warm plastic. It still amazes me. Remember my first time doing one of these load tests, I'm just waiting for that glass to start breaking, but I have yet to see that happen, any of the modules that we've tested. So if this is meant to simulate snow load, which of course we have tons of in Florida, wind gusts, or even just normal windy conditions. It doesn't have to be hurricane related, but these are certainly qualified to work in hurricanes. And while we're doing all of this, we can take flash tests, we can take images and see the module's bending, what's really happening, how much does it really matter. There are different ways to install solar panels, so we can simulate those different ways by moving the support clamps. And we can take it a step further by putting deflection sensors on the back, so we we can visualize how that module is bending at different pressures and with different supports. So I really like these images. On the left, we are applying more and more pressure onto a panel and seeing, you can see how it does. And on the right, we're going through hundreds of cycles of a smaller pressure. And just as a note, of course, I'm not going to pick the panels that don't crack at all to show. So these are not, I would not say these are representative of what we're seeing in the field. These were experimental panels that were sent to us, but they sure make for a nice image. So one of the techniques that's been emerging more and more recently is ultraviolet fluorescence imaging. So this is a technique that we've done indoors and outdoors. It's the only method where you can image the polymer components. You have the front sheet, the rear sheet, and for a lot of panels, you have another polymer sheet on the back sheet, creative name. And so if there are different defects that the panels go through, and depending on the materials used, you can see different features that give an idea of how that module is performing. In this case, looks like something might have struck this panel. This one is from the Florida Gulf Coast University. So chances are a hurricane might have thrown a rock at this module. And we can see all those cracks propagating. So yeah, I won't go much in depth on UVF, but there are different features you can see, different patterns that can appear, like a ring or just what we call a square or rectangle pattern. And that has to do with the components within the polymers that optimize optical properties and protection of the cell itself. Infrared imaging, this is one I think we're all familiar with. In the field of solar, this is one of the most common techniques to inspect panels outside. It's nice, quick, easy, and I like the pictures. So you can see whether cells are operating at elevated temperatures. That could be because of issues within the cell itself, in the bulk semiconductor, or it can be because metal's corroding. There might be a hot spot because there's one piece of that bus bar or ribbon that was soldered incorrectly. So now it's high resistance, high heat, going to damage the cell. Most of the images that you'll see are where you're looking at the front of the panels, but you can also look at the back of the panels. That's actually a pretty common technique too. But also IR imaging in the field is used to look at the power electronics too. If you've got an inverter that's extracting that power for the grid, your home, whatever, you can see what components might be too hot. You can look at connectors, and one challenge in solar is keeping is good quality connectors. So it's very quick and easy to take an IR camera and see if a pair of connectors is actually connected properly. There's a good connection there. And one final thing I'll note is depending on the pattern you're seeing, you might actually see parts of that panel that aren't really doing anything. In the case of this bottom left image, the top two rows of cells were not contributing power. So there's something in solar panels, they're bypass diodes that act as a protection against issues like this. So decades ago, before bypass diodes were used much, if you cover part of the panel, the entire thing is just dead. you're not getting any power out of it at all. But with bypass diodes, you can start sectioning parts of the panel, and if one of them starts going bad, you're not losing out on the other parts. So with IR imaging, you can see if there are any parts that are going bad. So this tool was developed by an instrumentation company called Tau Science, and in collaboration with the National Renewable Energy Laboratory. The idea behind this tool is that you have this gantry that you can put on top of a module, whether inside or outside, and it'll scan through every cell in the module and take a few different measurements. I mentioned UV fluorescence, photoluminescence, and non-contact EL, electroluminescence. So what it'll do is it'll take one flash on the entire cell for the photoluminescence, and then for the non-contact electroluminescence, which you normally need to probe, there we go. You flash half of that cell, and the power that's produced in that half acts kind of like an injection into the other half. So like with typical EL images, we'll pump in power into the panel to get that light. This is doing something very similar, just within a cell itself. Now, we've got all these measurements, we've got all these panels. We can tell how much power there is. Oh, is it low current? Is it low voltage? Why is the power not as high as we want it to be? So we can take this data and see the how of the performance. But if we want to understand why it's performing the way it is, we need to probe more deeply. So with this coring process, we take out pieces of the panel, clean it up, prepare it nicely, and do different measurements for microanalysis. In this case, for electroluminescence and photoluminescence images, we can find regions that look interesting, take them out, prepare them, and do things like scanning electron microscopy, which is down at the micron scale, and do some different chemical analysis techniques where we can look at not just the surface chemistry, but even like what compounds are there, what elements are there, even the energies of those bonds to give us some idea of what chemical reactions might be happening or have already happened. And all of this is to inform why did it degrade, what are the mechanisms behind why a solar panel is doing well or not doing so well. So with that information, we can go back to the industry and say, hey, these materials aren't doing as well as you thought, or these materials are doing really well. Let's keep doing this. We get all this information just to keep up the cycle of learning and continually improve solar panel technologies. So this is a picture of some of our team. We have plenty of others who couldn't make it to the picture. These are some of the utilities, companies, national labs we've had the privilege of collaborating with. And right on time. I look forward to any questions you have. Thank you.
Thank you. Let me do that.
Thank you.
We give them a... Thank you so much for a great talk. Let's give me a big round of applause. Thank you. Any questions? Any questions? We're busy with eating and listening as well. I have a question for you. I saw you use the machine learning to do the modeling. So I'm not very familiar with the machine learning thing. So how reliable the machine learning model would be? That depends on what the size of a data set you feed to your machine, to your software or something. How reliable the machine learning model could be?
Yeah, that's a good question. So we fed it 17,000 annotated images, cell images like here, and we saw around 90% accuracy. Now the accuracies are different depending on what classes of defects we use. A large part of what impacts that is class imbalance. So these defects are lumped together into different classes, and the output, the prediction is largely going to be as good as how many annotated images you have. So for some of these, we didn't have a lot of images that showed these defects, so they didn't do as well. Right now, we're actually working on applying this model to a larger set of images that we have.
So the images, I'm sorry. So the images means based upon your own the test, the experimental result, or you collect online or some literature, or where you get it?
Yeah, so these are all images that we've taken.
Oh, you take it. Okay, thank you.
Yeah, it's from a combination of panels that were installed outside or had gone through specific stress tests. And we had plenty of images of just off the production line, nice pristine modules.
Oh, okay, thank you. Additional questions. Looks like you guys more care about the mechanical durability, right? Because you apply the pressure on see how much the pressure your module can handle.
So that's one part of our research. I didn't have a slide in here, but we do have an outdoor test bed with high voltage capabilities. So the past few years, we've been studying high voltage degradation on some contemporary modules. So here we've got the high voltage and the mechanical loading, but we also have partnered with testing laboratories looking at other types of degradation, like metal corrosion, or even other types of high voltage degradation.
Okay. So, yeah. Anybody have questions? Do you have questions, Alan?
When he was talking about UDF analysis, or the UDF image analysis, yes, that. Yeah.
There you go.
And how different phenomena cause different kinds of damaging. What gives you the most bizarre pattern?
That's interesting. Most bizarre. I would probably say where my cursor is. We call that bright line or bright cracks. So typically, I'll use this top one as an example for this. So in this case, the compounds in the encapsula on the front side, they start breaking apart. So that's why we see the fluorescence. So if there's a crack in the cell, well, now there's an opening for oxygen to get through. And that oxygen will react with moisture, temperature, and sunlight to, we call it quenching those compounds. So that's why it appears dark. And that's what we typically see. But there are some weird cases when we've seen those crack lines are actually bright. And the weirdest thing is when in the same panel, we see dark and bright crack lines. That one we're still looking into, why that is.
You give another big round of applause. Thank you so much. Thank you. And this summer, we will send the 2 students over to your center to do the summer internship.
Sounds great. Yeah.
Thank you so much.
Thank you again for the opportunity.
Thank you. Dr. Senior, do you have anything?
No, that was pretty well done. Thank you, Dylan, and
Yeah.
thank you, everyone.
Thank you, guys. Thank you, guys.
All
And
right.
see you guys in the summer in person.
Yeah.